So let us consider a situation in 2 dimensions where we've got a constant force that only points in one dimension. So here's the situation. I don't have a ball, but this could be a ball. There's assuming that it turns out that the air resistance force gets a lot bigger if the speed gets bigger. And at small speeds, it's not totally unreasonable to neglect it. So if we say that air resistance is negligible on this, it would be better with a ball. When I throw this in the x direction, I'll throw it in the plus x direction. There still is a force acting on it. It's the gravitational force due to the Earth. But that's approximately constant near the Earth's surface. And the momentum principle tells us something interesting about what we should expect under these circumstances. So let's see if we can predict what we should be seeing here. So we're going to consider the situation in which we've got a ball on the ground. It's a soccer ball. You kick it with an initial velocity that has both x and y components. We're going to assume that air resistance at this speed is negligible. The usual coordinate system. Which of the components of the ball's momentum are going to change in the next half second? Use the momentum principle to think about this. So we're basically assuming that the only force on it is in fact the force due to the Earth. So 50% 2 and nearly 50. So half the class says p sub y and the other half says either x and y or maybe also z. Now, the momentum principle really has something important to say about this. And we need to think about what it tells us. If we write the momentum principle this way, P future equals P now plus F net delta T, we could rewrite this as P future X, P future Y. We can just write out all the components. That's a Z. P initial X, P initial Y, P initial Z, plus F net X, F net Y, F net Z, delta T. We add vectors. Notice what we're going to be adding. We're going to be adding this to that times delta T. We're going to be adding this to that times delta T. We've really got 3 separate equations here. It says that we could write it as Pfx equals Pix plus F net X delta T, Pfy, P initial Y plus F net Y delta T, P final Z, P initial Z plus F net Z delta T. Okay, you're going, yeah. But notice what's not there. Notice that the Y component, the future Y component of momentum only depends on the Y component of the force. This component isn't here. That component isn't here. The final X component of momentum only depends on the initial X component and the X component of the net force. It doesn't depend on the Y component. So that's just writing out this vector equation. And since this vector equation describes the way the world works, the prediction it makes is that, in fact, only the y component of momentum should be changed if the net force is only in the y direction. So that's interesting. And that's nice, because actually life would be extremely complicated if the x component of momentum changed by y were changed by forces in the y and z direction. Then we wouldn't be able to write simple vector equations like this. We'd have to have big matrices in there with how the y force changed the x momentum and how the z force changed the y momentum, and that's really nice that we don't have to do that, because that would be really messy. So we are very lucky that nature works this way, because it makes our lives much simpler when we're trying to predict motion. So what we're going to do now is actually make some predictions, and we're gonna work on predicting the motion of a ball. And just to warm up, we'll do something numerically. Let's start off with a little numerical prediction. What was the answer? Well, what was the answer? Okay? After this discussion, what is the answer to that question? 2. Only the y because here's the ball. Here's the gravitational force due to the Earth. There aren't any other forces. Air resistance is negligible. It's only down. Only the y component changes. So 2 is the answer. So let's see how that plays out numerically. If the ball's mass is 500 grams, we know its initial velocity. What is the net impulse acting on the ball during the next 0.5 seconds after you kicked it? The net impulse. Remember what's impulse? What's impulse? F net delta t. Impulse is F net delta t. So what's F net? Okay, so F net is in the x direction, 0. What is it in the y direction? It's negative because it's going down. And that's the magnitude, isn't it? mg. So we need the mass, which is 0.5 kilograms times 9.8 newtons per kilogram. And 0 newtons. And what's delta t? Half a second. So we have, that's going to be just a little under half of 10 is nearly 0.5. So that, and then we have to multiply by another 0.5. And so we have F net delta t is going to be 0. We have 0.5 times 9.8 times another 0.5, 0 Newton seconds. And what does this come out to? And there's a negative sign, isn't there? Yeah. So it comes out to 0, negative 2.490 Newton seconds. Well, what's the force? Gravitational force involves a mass, doesn't it? Okay, this is not a big stretch. This is something you need to be able to do. So other questions? Okay, given that, during this half a second, which graph shows p sub y for the ball you just kicked? You just calculated the net impulse, so you calculated the F net delta t part. And you know the initial momentum, the initial velocity was 370 meters per second. So we're just looking at the y component of momentum. Yes, 4 is correct. And how do we know that? Well, the initial value of y component of the momentum was positive, wasn't it? 3.5 kilogram meters per second. So that rules out 2. And there was a decrease of 2.45. So we subtract 2.45 from 3.5. We're still going to get a positive number. So that means it doesn't cross the axis. And this is the only graph that starts out positive, goes down, stays positive in that time interval. Would it cross the axis? What does it mean when it crosses the axis? It's changing direction, isn't it? So it's not going up anymore, it's going down. Right. Yes, so unless it gets caught by somebody up in the air, it's definitely going to start back down. So here, to predict the motion of the ball, we do exactly the same thing that we've done before, and this is what it would look like graphically. So here's the ball starting off. The blue arrow is going to be its initial momentum. The red arrow is the gravitational force. So we need to calculate an F net delta t. We need to get the impulse. And so the impulse is going to be in the direction of F net. And that has the same units as momentum, Newton seconds, same units as kilogram meters per second. So we're going to add the momentum now to F net delta t. And we're going to get a new momentum. That's the sum, the vector sum. And then we're going to use that to figure out the velocity. And now we're going to do it again. We took one time step. So now we've got the current momentum. The force is still the same, pointing down. So we're going to get a new impulse pointing down. That's F net delta t. And we're going to add it. When you add vectors, you're putting them tail to tip. So that's the new momentum there. We can use that to get a new velocity and let it move. And then we're going to do it again. And we get an F net delta t, and an F net delta t, and an F net delta t, and an F net delta t. And because the force is constant, we're always adding exactly the same F net delta t every step until it hits the ground. And then, being a stupid computer, it would be happy to go on doing the calculations. So we need to tell it that it needs to stop at that point. But that's basically what we would do to predict the motion using this iterative scheme.